As usual, run the simulation and watch carefully what happens. Okay, what you should have noticed is that it appears to go at a constant velocity until it reaches the green area, which is the rough surface, and then it slows down and stops. And if you were watching carefully, you'll notice it stopped before the clock stopped. So keep that in mind. And to get the final velocity is 0, you need the initial velocity. You can measure that. And good practice would be to measure it in 2 different places to make sure you get the same result. So you could measure it for the first, how far it goes in 1 second, and how far it goes in the 1.5 seconds. The momentum of the box is constant, so it's telling you it's constant, but I would check it anyway just to make sure, and then you'll have 2 readings of velocity. So try that. Once you know what the initial momentum is, you know the final momentum is 0, you can calculate the change in momentum, final minus initial, right? And it's going to be negative because the final is 0 and the initial is a positive momentum. That makes sense. It lost momentum. And you know that the impulse is simply equal to the change in momentum. Same sign. And you know that the impulse is equal to the average force that acts over the time interval that it acts. And the force acts when? From when it touches the friction surface, the rough surface, till when it stops, right? And once it stops, then friction is no longer an issue because it's not sliding. So those are all the things you have to measure, and with those you should get the answers that are posted. And you are told that the momentum is constant during the first 1.5 seconds. So 1.5 seconds, it encounters the rough surface. And so that's when you should start the time. But remember, again, you want to very carefully determine when the box is completely stopped in order to calculate the time interval over which the force acts. All right, let's watch. 2 carts move together. One hits and sticks, the other bounces back and goes off screen before the clock stops. Okay, so they both go in with the same velocity assumed to be constant, but again you can measure the velocity over half the distance and then measure it over all the distance just to make sure you get the same number. It's a good idea to do it twice over 2 different intervals just to make sure it's constant and there's no acceleration. And the upper cart, the momentum ends at 0, right? So it has a negative momentum going in. They both have negative momentums going in because this direction is negative. And they both have the same momentum going in. But this, P final, is 0. And for the bottom one, P final, you have to get the velocity. And if the velocity goes back at the same velocity, what does that mean? That means that there's no change in kinetic energy because the velocity is squared. So momentum is a vector, but energy is not. So if it goes in at a certain velocity, comes back at a certain velocity, what happened? It means that the energy got stored in a spring and then got put back into the cart with no energy loss, and kinetic energy is conserved. If it goes in with a certain velocity and goes back with less velocity, then it's still an elastic, it's still partially elastic collision or partially inelastic, which means some energy was lost, but not all the energy was lost. So the key thing here is getting those velocity measurements correct. Okay, let's watch. Notice we have the time and the velocity. Velocity is constant. Collision happens, velocity changes, and then remains constant. So it's an inelastic collision. The two objects stick together. And by using conservation of momentum, we can find the mass of the car. And we don't even have to measure the velocity, so this should be pretty straightforward. P initial equals P final, or I could write it as Px initial equals Px final, since this is all horizontal. And so we have the mass of the truck times the velocity of the truck plus the mass of the car times the velocity of the car, but that's 0. And that has to equal the mass of the truck plus the mass of the car, all times the final velocity squared. And this, the final velocity of the two things, right? Not squared, what did I say? So that's given. You can see it right there. That was given if you go back and run the animation. The mass of the truck is given. The mass of the truck is given. You just need this. So do the algebra. Don't put the numbers in. Divide by V final. And then subtract the mass of the truck from both sides. Algebra, right? And then you see what you're getting. Can you see the algebra here? Mass of the cart equals the mass of the truck times the initial velocity of the truck divided by the final velocity of both of the things minus 1. Okay, let's watch. You see we have the velocities of both objects, and we can see those velocities are constant, and they change and remain constant after the collision. So we have the velocities before and after of both balls, but we're not given the mass in the simulation, but I gave you the mass of the black ball. So when you calculate momentum, that's the mass times the velocity. It's a vector, positive and negative, right, depending on the direction. But when you calculate the kinetic energy, so to calculate all those values, and that's just a positive number, you need the mass of both objects. So use conservation of energy to find the mass of the red object. So do a general, see if you can do a general solution for what the mass of the red ball should be. Just a general symbolic solution. Try to do that using conservation of momentum and see what you get. So there's the conservation of momentum, and there I wrote it out, and I'm just leaving all positive signs. When you put the velocities in, if they're negative, you'll put them in as negative and positive. But we want M2 So just do the algebra and solve that equation for M2 and see what you get. So isolate the M2s on one side and the M1s on the other side, and now when you bring the M1 over here, it has to become negative, and when you bring this M2 term over here, it has to become negative. And now just factor out the M2, factor out the M1, and solve for M2. That's the final 2 steps of algebra. See what you get. So I wrote it up here. Hopefully I didn't make a mistake in algebra. I factored out the V2 initial minus V2 final. Put it in parentheses, and then I had divide by that on both sides, and factor out from the N1 the V1 final minus V1 initial. That's in brackets. And so there's the whole solution. That's your 800 grams. You put the velocities in there. And remember, if a velocity is negative in the simulation and it's negative here, it becomes positive number, right? Because my original equation didn't account for any negative values. So if you get all your negative signs correct and you put the numbers in here, you should get the correct value of M2. And once you have the correct value of M2, you can calculate all those quantities asked for. Okay, since you're here, I'll help you out. This number is negative and this is positive, so that's all negative, so the numerator is a negative 3.33 repeating, or 3.33, and this is a negative number because it's going left, and this is a positive number, so those two are negative. So anyway, this comes out to be a factor of a half, and so the mass, the red mass, is half the mass of the black mass, and that explains why its change in velocity is double that of the black mass, because it's only half the mass. So M2 is 400 grams, and with that you can do all the calculations and get them correct. Okay, next you see you're given the mass of both carts. It's going to track the position and the time, and if we play it we see like, okay, boom, the spring goes apart, they drift off, they look like constant velocity, but let's go back and use the stepping button. So you see nothing's happening, so there's a dead period here. Nothing, still nothing. Oh, there it goes. At 0.2 seconds it releases, and now this counts every 0.02 seconds, and if you look at the position of the green one, it's 0.44, and the red one 0.46, and if I step the button it goes to 0.46 and 0.49. So you see the green one increase by 0.02 in 0.02 seconds, and the red one increased by 0.03 in 0.02 seconds. Let's see if it's constant. So if we go another step, the 46 should go to negative 48, and the 49 should go to 52. Aha. And then the 48 should go to 50, and the 52 should go to 55. So you see with the stepping button, it makes it very easy to see that each increment of 0.2 seconds, the distance changes by the same amount. So the velocities go off. Just remember, the green one is a negative velocity, and the red one is a positive velocity. And with the mass and the velocities, you can calculate everything. Okay, we're ready to do the last one. Let's see if I can get it. Alright, animation 812 has 5 different animations, and it's two-dimensional collision. And you have an angle measuring tool here that you can drag around with your cursor, and you can also measure the position of balls, and you're also given the velocities of the green and blue ball. So you have a lot of information, but you will have to measure angles. And you do need to keep in mind that when we go into 2 dimensions at P initial, Px initial, we have to separate out the components. Px final and Py initial will be equal to Py final, just like we did sum of the forces, right, equals Ma. We have to separate it into sum of the forces x equals Max, and sum of the forces y equals May. Just like we had to do that for forces, we're going to have to do that for momentum. And so you're going to have to get the components of the velocity and do these 2 conservation momentum equations separately. Alright, make sure you watch all the animations, but the 2 that we're going to do, 6 and 7, is animation 1. So let's look at animation 1. Okay, can you see it? Is it running? They collide and they go off. So you see the velocities are given. You can get positions and times, and you're going to have to measure the angles to get the components. Let's see if we can get animation 4. Okay. Looks very much the same, but the masses are different. Notice the masses are different in this. So you see the angles are different. Stop it. Go back to 1. You see in 1 the masses are the same, and they go off with the same angle. So anyway, and also remember you can move this thing around to measure angles and change it so that you can measure angles. And when you put your finger in a position, you can get positions. Alright, hopefully the exercise itself will guide you through the rest of it. And one last item, the sort of end of the video table of contents. If you want to just go to one of the problems, these are the times at which they start. Alright, good luck.